design practice module 22. In the last few modules we were looking at a very interesting case study by the CALS CE electronic system working group about how you set up a concurrent engineering environment and what kind of direct applications of resources you could kind of plan so that the level of the concurrent engineering environment moves up one grade. So, when we talk about such a system is in place, how do you actually record or measure, or how do you actually find out whether the CE system is effectively sort of implemented. So, there are a variety of techniques which are useful for implementing the concurrent engineering environment, and I am going to now take case by case some of these techniques which are important for you to understand how a CE is really practiced from product design all the way to every part of the life cycle of a product. So, we will now discuss some techniques for implementing the concurrent engineering philosophy, or for making. So, we exactly know what is it that needs to be pumped with resources in terms of elements, but we do not know how to implement, and so therefore, it is important that we get an understanding of this process. So, there are few of the techniques which are very commonly used in a CE environment for implementing concurrent engineering philosophy. One of them is actually adding robustness to the product design. So, this was proposed by Taguchi, which really is about learning from mistakes in terms of non-compliance to standards or specifications, and trying to do some improvement in the design through a organized cost structure, so that one can in fact determine or one can in fact make take decision making regarding or arrive at decision making regarding whether a certain cost structure needs to be included in a process for ensuring compliance to some specifications or some standards. In context of that, there are a few other techniques which are important for me to discuss. One of them is called the failure mode effect analysis. We will try to look at this aspect and how from a systems implementation point of view, FMEA can be utilized for eliminating a process defect through design improvements. Then there is also a very interesting tool called quality function deployment or house of quality, which is used for really mapping the exact need which comes directly into the CE environment, in fact need that exists out there in the market for which there is a product definition. If you go a little bit further, you have this very interesting Kano model which talks about mind of the customer. Quality function deployment is really about the voice of the customer, but here this is about how exactly he would be delighted. So, there is a delight factor over and above what basic functionalities this tool right here would serve. We will also talk about the interesting area of axiomatic design and then design for manufacturing and assembly, and some aspects of group technology which may be needed to understand for thoroughly implementing a concurrent engineering environment. So, let us start with robustness, and robustness, the term robustness really comes with the term quality. And so, if we look at the product cycle really, and if we wanted to see how quality can be improved or what is the purpose of the quality to be improved, we all know that in today's competitive business environment, it is very, very important to deliver products that meet exactly the customer requirements. Okay. And requirements could be in terms of the functionality, the quality of the functionality or quality of the product itself. It could be in terms of cost, overall cost. It could be in terms of maintaining schedules, delivery lead times for example. And not only that, in today's framework of all enterprises, the management philosophy really aims at how to continuously have a sustained product quality improvement program. So, what are the opportunities which are there to improve product quality in any product life cycle? Let us say if we look at a life cycle, it really starts from the design stage, product design stage. Then we talk about a process design once the product design is kind of established. We also talk about production phase. We also talk about maintenance and product service, which is after sales phase, and then finally a very important disposal phase, which is not mentioned here, but I will just add it here, product disposal phase. So, these are different aspects of product life cycle, and the design should be done at ab initio steps in a manner, so that it builds the quality right at the very beginning. So, quality is built at the beginning. So, what I mean really is that can the specifications be set to an extent that it gives an useful know how about what is the capability of a process that is already there, where little addition deletion may enable the process to start generating new products. Okay. So, you are basically learning from the improvements that need to be done in the design, so that, or changes that then need to be done in the design, so that it suits the process design. So, it is basically adding more and more value, I would say, to the design. The initial stages itself making it more robust in nature. Robust meaning there are hardly any failures along the way of the product cycle, from the design to manufacturing to sales to after sales and disposal. The product goes smoothly without having to go through any hitches, and so therefore, that is what we know by robustness, we mean by robustness. So, adding robustness to the design, so that it survives the life cycle. The preferable approach therefore would be to improve the product quality by building quality into the products itself, okay, at the design stage itself. And this is followed by obviously improvements at the process design stage, so that there are certain fits which you can make. You had done that example of how a shaft could be manufactured over a series of lathe machines, and we learned how to have the right manufacturing option assembled for the right specification, so that amount of scrap produced is minimalistic. So, that is about how you can improve the process at the design stage itself. And then of course, you can have these improvements coming from all the different steps like production, engineering, maintenance, product service stages, so on and so forth, which builds in the necessary amount of robustness. So, when we look at product product design, that it is a prime activity in the process of realizing any product, and therefore, this design really would have the greatest impact on the quality of the product. And whenever there is a deviation in this quality, there is going to be some kind of loss associated with such deviations. Although this loss does not really come on a balance sheet, but these losses are notional, and if these losses come in, it gives you an idea about how to proceed, so that you can do some loss minimization. Some numbers are there rather than just qualitative indices, and therefore, it is a very good strategy to monitor the deviation of all the functional characteristics of products from their target values through adding notional losses to quality. So, in fact, Taguchi, when he started applying this process, he proposed a philosophy and methodology saying that designing quality into products and processes should be at the very beginning. And he postulates that a process of designing a product or a process should be viewed in terms of a system design phase, parameter design phase, and tolerance design phases. So, of course, I will come into the details of all these different techniques. So, just before going there, let us learn a little more about the different losses which are there in this aspect of quality degradation because of deviation from target. So, one of the most important aspects of the product development process is to translate the customer requirements into product specifications, and obviously, the main goal here is this one term right here, the product specifications, which are arrived at through a meticulous process of product design. And obviously, the manufactured products which are there and not meeting specifications should either have to be repaired, or they have to be completely rejected, or the market kind of does not accept them, and they are losses. Okay. So, the prime quality costs for supplying satisfactory products to customers include sort of producing, identifying, avoiding or repairing the products which do not meet such customer expectations, so or requirements. So, if there are certain preliminary issues which have cropped up in the products which have made them non-compliant to what exactly is specified as to how a product should be produced, then obviously that is not acceptable, okay, for the end user who is the customer. And therefore, one can levy some of these notional costs onto the system in a number of different categories, where these costs would kind of guide you through giving you a lead into what has to be improved at every stage, either the design or the product itself or the process itself, or anything related to the different phases of the life cycle, so that this end user satisfaction index goes up and you are compliant to what is needed. Okay. And so, it is basically about what do you need and how do you satisfy the need, are you satisfying the need accurately or not. So, we are giving you sort of a quantitative basis to do that. And so, if I looked at different kind of costs which are available in different categories for describing the quality, there could be costs related to prevention for these non-specified or for this deviation from targets to happen. There can be costs needed for sort of appraisal, for example, measurement costs. There are parameters to be measured of produced items where after measurement you find there is a deviation. So, that appraisal has to be done in a continuity. There is also something called an internal failure cost, which has to be absorbed once a system has been already partially built. Let us for example, look at a car making facility. If you have already produced a weld body just up to the final stages, and then you realize that you have a spot dent, then the whole body is lost, and it is an internal failure cost which happens, which comes to the business in fact, and then either you have to somehow repair it offline, or if repairing is not possible, then scrapping it would mean a humongous amount of metal has already been wasted into the, which goes into the car body. Similarly, there are external failure costs, and these are in fact more prestige issues when such failures happen in the market, which is related to giving a lot of poor visibility for the company's quality, or also maybe in terms of some losses of market share, etc. So, what has to be done in order to levy the costs at the right time, so that these costs do not prop up really a lot, and they get controlled at the very outset, by complying the standards which are sort of made. So, let us look at some of the details about such costs and how it can be prevented, okay, or from happening. So, particularly prevention cost, it includes all the efforts that go into designing and manufacturing a product that meets some customer requirements. Okay. And so, prevention cost is the cost you add on to the system to prevent the non-compliance or the non-conformance. There may be various elements of prevention costs, which may include activities involving, let us say, quality planning at different phases of the production or production engineering. There can be something related to the new product reviews, which gives you an idea about how a product is doing in the market, or what are the expectations of the customer, which way the market goes in terms of reliability, aspirations developed by the customer, so on and so forth. There can be also some kind of cost put into do product design or process design in an appropriate manner, in a robust manner, so that failures do not happen, and automatically there is the right mapping of the right capability that you have in terms of manufacturing options to the right designs that you are going to manufacture. There could also be prevention in terms of accurate process control. This needs for a strategic way of monitoring, measuring, recording, and then trying to statistically analyze whether we are in control or out of control, or whether it is needed to do something to the process so that it comes back into control. So, all those costs which are levied because of such activities fall under the category of prevention costs. There could also be components related to training of individuals who are new to the system, so that they do not do any non-conformance, or let us say even things related to quality data acquisition, either automated or in a manual manner, or some kind of an analysis from trends which leads us to believe that, and this is also known as prognosis, that something will happen at a futuristic point of time related to a product. So, you are preventing a failure much early to actually the failure started happening. This is done a lot in aerospace industries these days for meeting up health monitoring aspirations, engineering aspirations related to such products. And there are also appraisal costs. Appraisal costs are typically inclusive of those costs which are involved in measuring, evaluating of whatever we are producing, or even sometimes auditing the products to see if they are as per the norms, they are as per the specified requirements. There could be costs involved in, again, inspection of or auditing of the individual components, or sometimes purchase material from vendors which directly go into the assemblies. And to ensure the conformance with standards and specifications, there is always going to be this essential measuring, recording, and sort of using this for policing purpose, so that the process stays in control. So, that is called appraisal cost. It typically includes cost of activities such as inspection, for example. This is of course a non value added component. In fact, in the latest process designs from particularly Japanese manufacturers, inspection has been almost combined with the process itself. So, that the idea is that outside the assembly line or outside the final product line, there should not be any unit which goes in an uninspected manner or in an undetected manner. So, this is a part of so called total quality management, TQM, that people perform. Okay. So, then you also have tests of incoming materials, you have product inspection and other tests, you have materials and services consumed and maintaining accuracy of test equipments. All these levy costs, and they are just because you want to appraise the system of what is the quality level. So, that is why appraisal costs. Internal failure cost, as I told, occurs when the product fails to meet customer requirements before being shipped. So, something has failed within the domain of the production itself. So, there is still a control of the processes and still there is a scope of improvement quickly. So, these are not that serious in terms of putting a lot of bad name and affecting the prestige. But yes, internal failure costs sometimes are very critical, and how you handle them and what kind of awareness level you create is definitely the most important management strategy which enables one to zero down the failures within the ambits of the production facility. So, internal failure costs include all costs involved in rectifying the failure which has happened. You can have examples of, for example, internal failure cost elements could be out of failure analysis, out of the scrap generated, what are the kind of repairs that are being met. A product like an automotive is made and there are 20-30 defects in that automobile after it rolls out of an assembly line. So, it is obviously an additional cost that you are putting in terms of repair time, so that all these different defects could be successfully repaired. So, it is non value added and therefore levies a cost again, and there may be a failure if left unrepaired and sent to the customer. So, there are costs related to, for example, retesting of something which has happened. For example, there is a door noise or an instrument panel noise. So, you might have to just go through a process of iterative testing and repair, so that you finally arrest these problems. Failures could be related to downtime of equipments, which causes major problems in schedule issues related to, remember, schedule is also a very important part of customer expectation or requirement. There are also yield losses sometimes and downgrading of usual specifications, because just because the specifications maybe are too tight for under the existing manufacturing environment, and unless you downgrade them, there is a possibility of almost all failures happening to whatever is produced. So, these are all because there is improper planning, because of which some of these failure costs would come. External failures on the other hand are very serious in nature and consequences. It's basically something related to directly when the products do not function satisfactorily at all after being supplied to the customers. So, there are many activities to do this compliance adjustments. For example, sometimes products are returned back under warranty and there are warranty claims issued to the company. It actually goes into the balance sheet of the company. There are other costs which are liability costs. For example, some accidental casualty has happened because of use of a product because of its failure. So, that is levied on the particular manufacturer. So, one has to be very careful about these external failure costs as well when you talk about maintaining a general or regular system of quality. So, when we talk about the other issue, that is the Taguchi's approach for building robustness in a manner, we want to specify the design steps in a manner so that we have a system level design, we have a design of parameters, and then of course a third level which talks about the tolerance design. And here we would like to use system design as a process of applying scientific knowledge to produce a basic functional prototype. Okay. This can be typically a phase at the very beginning of the, let us say, product designing process, where new concepts, new ideas, methods are synthesized and they provide new or improved products to the customer. This means that the basic design concept is established during this phase, including selection of the parts which are involved in the design or the materials or the sub-assemblies. Let us give a small example that you are designing a car and the following questions need to be addressed, like should the internal combustion engine block be made out of material cast iron or aluminum alloy, depending on what is the weight requirements. Should the brakes be anti-lock type? That is another question that we need to address while doing the system level planning or designing. So, we are talking about a functional system layout, maybe just decomposing the various functions in terms of subsystems and then using these subsystems to sort of connect to each other to create a functional map. So, that is the first phase of any sort of design activity, and it really yields into the overall layout of the nitty-gritties behind a system which is planned to be designed. So, the relationships between inputs and outputs also are established in such subsystem level as well as the overall system level, and functions of parts and subsystems are determined during this phase. So, you have already done some mapping related to wagons and carts earlier in the first few lectures when you talked about just laying out functionally decomposing the system, okay, into various subsystem level information. So, once this level is crossed, we go to the next level, which is the parameter design phase. So, where the levels of the products or process design parameters are set to make the system performance less sensitive to causes of variation. Here is an aspect of non-conformance which is being embedded in this statement. Obviously, causes of variations are deviation from the target, and if you want to create design parameters which would randomly yield a variety of such noise or deviation from targets, then obviously it is a low quality design, it is a less robust design. But the idea here or the goal here is to introduce as less variation as possible to the performance of the system that has been planned in the last step by setting the parameters related to processes or related to the products at the right levels. So, in parameter design, maybe wide tolerances on noise factors are assumed to allow low manufacturing cost. Okay, it is quite costly to control noise factors, as you know, but during the parametric design phase the quality is improved without controlling or removing the causes of variation. So, you are talking about setting up the right specification which will be producible. I will show you some problem examples later. With costs, you could actually try to determine what is the tolerance level or the specification related to a certain engineering product, just because you would have a living of greater cost while the component goes out in the market. So, a sort of a permanent cost put in the process for carrying out a small check or an inspection might just change the paradigm and create the system or make a system which is lower, in terms of its sensitivity to variation, and you could address the problem right there in the process itself. So, there are a lot of methods which are used in this particular parameter design phase. For example, DOE, design of experiments, are very widely used to set up what is going to be the right set of parameters, which would help you to operate at a low noise level. There are also simulations and optimization packages which are used as techniques at the parameter stage to set up some parameters related to a system. And then of course, the third phase that Taguchi suggests in order to build robustness into the design are the tolerance design phases, where it usually follows the parameter design phase, but here the basic purpose is an improvement in the quality by tightening tolerances around the chosen target value. So, whenever there is a huge deviation, you might be able to design the process or maybe the specification in a manner, so that these tight tolerances around the target values may help guide the right quality to be produced. Okay. And choose the control factors which are available to the designers in a manner so that you reduce the performance variations. I will come to this when I exemplify a case of let us say steering control on a car, and I will show you how these different factors would influence the overall design. So, overall the quality improvement must happen in terms of reduction in quality loss, which is a notional loss again levied upon the system. And although there may be an increase in the manufacturing cost, the lessening of quality loss in a way would be helping you to guide in the right manner, so that your variation or deviation from the targets are as less as possible. And so, this is where the aspect of robustness builds in the design, that if your variation of a system matching to the right process is minimized, you are successful to add robustness to the design. There is not going to be any kind of non-conformance. These are all linked. Usually the customer is the one who judges, and so if the customer does not get any non-compliance, he is happy, and that is the goal of everybody working in the business, including the designers as well as for the product as well as the system and the process. So, let us now look at the approach of how we penalize in terms of giving some notional losses as there is a deviation from the target, because this would be the basic tool used to set up the specifications, okay, or the designs later, or maybe doing tolerance design based on the quality loss. So, we will do that in the next step. So, in this particular case, let us start defining the loss function now. So, traditional understanding of quality loss is given in this particular figure, that you have two different limits, let us say the upper specification and the lower specification limits, and whatever is beyond these, for example, some particular component or system which crosses the USL or the LSL are considered to be 100% loss, they are rejects. So, basically you are rejecting the whole crossovers and accepting all this which is in this white area right here at the target or beyond the target by a distance of whatever specified tolerances have been given in the system. But Taguchi's loss function is slightly different, is basically postulates that the loss starts not at the crossover of the USL LSL, but right at the deviation stage itself. So, anything which gets deviated from the target levies a sort of a loss, although this is not an actual loss, because you are not going to waste the component, but there is a notional loss which comes to you, which helps you to sort of go ahead and modify yourself at an early stage, so that this situation does not come over at all. Okay. So, you can see that the overall loss level is reduced because you have a tightness of control. So, this is more about a management practice, I guess, which you are going to follow. So, this is what we are going to use for our studies, and we will try to find out based on this loss equation what is going to be the kind of average quality loss. So, let us suppose there are different measurements, let us say I measurements of this quality characteristic which is there, and these I measurements vary between let us say some 1 to n different measurements. this yi shows the ith measurement. So, in that event what would be the kind of average loss which will be levied on the system. Let us look at that, and then let us try to tweak that in terms of what are the desirables and what are the undesirables of characteristics. There are some characteristics in products which you might need to retain, for example, ultimate yield strength, the higher the better, okay, or there are some where it is a completely undesirable and you typically envision to operate at a value which is close to 0. For example, there should not be friction or wear and tear in components, they should be kept at a level of 0. So, the loss equation might vary, it is not that there is a target friction value which is there, friction needs to be at target 0. So, loss equation might slightly vary, and so does the average quality loss. So, let us actually have an understanding of all this from a standpoint that whenever such a loss is levied to the system, it will help you to improvise your design specifications, and you will get an emergent design which is actually robust enough to handle a situation like a failure situation like that. So, it goes without having a failure, because the right specifications could be imparted just after it crossed the target, okay, at the right time, so that it did not cross over a maximum threshold or something. So, let us look at average quality loss. So, in the I measurements that I have been talking about, the average quality loss would be defined as loss due to y1 characteristics plus y2 plus so on up to loss due to yn characteristics averaged out with respect to n measurements. And if I wanted to just use the Taguchi's loss equation about Ly equals k times of y minus t square here. So, obviously, for the average quality loss, we are going to represent this in terms of k by n times of y1 minus t square plus y2 minus t square plus y3 minus t square plus so on and so forth up to yn minus t square. And we would like to iterate this or algebraically manipulate this equation in a manner so that known quantities which are measurable related to, let us say, the mean for the distribution of these measurements or the sigma standard deviation for the distribution, they are utilized to describe what you call the average quality loss. So, just algebraically trying to solve this, we have y1 square plus t square minus twice y1 t plus y2 square plus t square minus twice y2 t, y3 square plus t square minus thrice y3 t, so on and so forth up to yn square plus t square minus twice yn t is what the average quality loss equation is going to be like. And if I try to group the squares together, for example, all the yi squares together, or for example, all the twice yit terms together or the t's together, we are left with 3 different terms here. So, it is y1 square plus y2 square plus so on up to yn square divided by n plus nt square by n. So, n goes off. So, you have only t square minus twice t by n times of y1 plus y2 plus so on up to yn. So, we all know that the y1 plus y2 plus so on up to yn by n, also written as 1 by n I varying from 1 to n yi, is the average mu for the particular distribution. And we have here a case where I can write this equation as y1 square plus y2 square plus so on up to yn square by n plus t square minus twice t times of mu. And let us suppose we try to convert this a little further by bringing in slight modification to this first term right here and recording this as y1 minus mu square plus y2 minus mu square so on up to y n minus mu square whole divided by n minus of, because there are exactly n mu squares which are involved, I will just subtract minus mu square and also add further twice mu times of y 1 plus y 2 plus y 3 plus so on up to y n divided by n to this whole equation plus t square minus twice t mu. So, that is how I am going to represent this whole equation, which is finally going to change into k times of n minus 1 by n times of sigma y I minus mu square, I varying between 1 to n, 1 by n minus 1 minus of a plus of mu minus t whole square. This right here is sigma, standard deviation. Okay. That is how the standard deviation for any distribution would be, and so we are left with an actual value which equals to k times of n minus 1 by n times of sigma square, I am sorry, this is sigma square, square of standard deviation plus mu minus t whole square. So, that is how we will record the average quality loss of a situation where a target value t is not achieved because of a certain mean and variance of recorded values around the target. So, this is exactly where the Taguchi's average quality loss, or how the Taguchi's average quality loss is calculated. We do record that in case n is quite large, then n minus 1 by n could be recorded as converging to 1, and so we have the loss equation in that case to be simply a summation of sigma square and mu minus t square times of k. So, the AQL will change once the n value or the subset of observations are quite large. So, I think I will bring my lecture, this lecture, to an end, but in the next lecture I will take it up and try to analyze the situation more from a practical standpoint, where we will see that based on the different quality characteristics that we are considering, this loss function will also vary, the equation will also vary, and we will start applying this for calculating specifications which would be important for the product design stage itself. So, thank you very much for listening to me. Thank you again.